Okay, so have you ever ridden one of those roller coasters with the big loop-the-loops?
Yeah, definitely.
It's such a crazy feeling, right?
Oh, wait.
Like, how do those things even work?
Well, that's what we're going to deep dive into today.
The physics behind those loop-the-loop roller coasters.
And we've got a really cool tool to help us visualize it all.
This interactive simulation called the vertical circular loop model
It's an open educational resource.
from Singapore. Lots of visuals.
Even lesson plans, if you're feeling ambitious.
But what I love about this simulation is that it brings these classic physics concepts to life
Like Newton's laws.
and energy conservation
We'll see how it all works together.
in a way that's totally visual and interactive.
So imagine you've got this virtual roller coaster track, okay?
And our simulation lets us play with a little mass.
It moves along different sections of the track.
You got a horizontal track,
An upward slope that leads to the loop itself,
then a straight bottom track.
and even a free fall section, just for kicks. It's like a digital physics playground.
Okay, so as this mass moves through the loop,
It's experiencing all these different
it's
forces,
got gravity.
always pulling it downward.
Right.
And then you've got the normal force from the track.
Which is like pushing back on the mass.
Exact.
So I'm imagining like at the bottom of the loop,
Yeah.
that normal force must be pretty strong.
Oh, you're absolutely right.
Because it has to like counteract gravity
It has to be strong enough to both counteract
to
gravity.
keep the mass moving in that circular path.
Yeah, that's what gives you that feeling of being pushed down in your seat on a real roller coaster.
Totally. Makes sense. So what happens as the mass starts going up the loop?
Well, as the mass goes up the loop,
Does the normal force decrease?
yeah, it starts to decrease. And the reason for that,
Because gravity is working against it now?
gravity starts acting against its upward motion.
Oh, I see.
So gravity's always pulling straight down.
Right.
But as the track curves upward,
Part of that gravity is now working against the mass's motion.
exactly,
So it starts to slow down.
it starts slowing down.
And the normal force decreases too.
Exactly.
Okay, now I'm really curious about what happens at the very top of the loop.
At the very top of the loop, if the mass is just barely making it through,
Yeah.
the normal force actually becomes zero for a split second.
Wait, so the mass is basically like weightless for a moment.
For that instant, the only force acting on the mass is gravity.
But why doesn't it, like, just fall straight down?
That's the beauty of physics.
Okay.
Even though the normal force is zero at the top,
Right.
the mass still has enough speed in the direction of motion.
There's still, like, momentum carrying it forward.
We call that tangential velocity.
Tangential velocity.
And that's enough to keep it moving along the circular path.
Okay, so it's like, even though it's slowing down overall, it still has enough, like, sideways speed to stay in the loop.
Exactly. It's like that classic example of swinging a bucket of water over your head.
Oh, yeah.
The water doesn't spill,
Even when the bucket's upside down.
even when the bucket is upside down because it's inertia
Whoa.
and that sideways velocity.
Okay, so as the mass comes down the other side of the loop, the normal force increases again.
As the mass descends, gravity now assists its downward motion.
Ah, okay.
So it picks up speed,
And it gets pushed back into the track.
and the normal force increases to keep it on track.
So it's like this constant push and pull.
Between gravity and the normal force.
That makes this motion so dynamic.
Yeah, that's exactly right.
This is making me think about that feeling you get on a roller coaster.
Uh-huh.
Like that shift between feeling really heavy and then almost weightless.
You're right on track. The greater the normal force,
Yeah.
the heavier you feel.
So at the bottom of the loop, you're pushed down in your seat because the normal force is so strong.
At the bottom of the loop, you're pushed down into your seat because the normal force is pushing up on you with more force than gravity.
Yeah.
Then, at the top of the loop, when that normal force decreases,
Yeah.
you experience that feeling of weightlessness.
Like you're momentarily floating.
Exactly.
That's so cool. It's like your body is becoming a physics experiment in real time.
You got it.
Now, what about the energy side of things?
Okay, so that's where the concept of energy conservation comes in.
All right.
If we assume there's no friction or air resistance,
Right.
the total energy of the system,
Okay.
that's the sum of its potential energy and its kinetic energy.
Potential energy being related to its height.
Potential energy, which is related to its height,
Right.
and kinetic energy related to its speed,
Speed. Okay.
remains constant.
So as the mass goes up the loop,
It gains height.
gains potential energy but loses speed.
It gains height and potential energy,
All right.
but loses speed and kinetic energy.
Okay. Precisely.
It's constant trade-off.
Like a seesaw.
You as a rider are experiencing this energy shift.
So as the coaster climbs, I feel that weightlessness potential energy is increasing.
As the coaster climbs,
Yeah.
you feel that sense of weightlessness as potential energy increases.
Okay.
Then, as you rush down the other side,
Yeah.
that's kinetic energy taking over.
So it's like this constant conversion back and forth.
It's like a constant conversion between those two forms of energy.
Yeah.
But the total amount always stays the same.
Like a physics magic trick.
It's a physics magic trick.
But I'm guessing in the real world, it's not quite that simple.
You're right. In reality, there are always factors like friction and air resistance
Right.
that can affect the motion.
Makes it a bit messier.
But even with those complexities,
Yeah.
these fundamental principles still govern the basic dynamics.
So we've talked about forces, we've talked about energy,
Yes.
but what I'm really dying to know is how this actually plays out in the simulation.
Well, that's where the real fun begins.
Okay, all right, I'm ready. Let's dive in.
We're going to dive into the nitty-gritty of the simulation
Okay.
and explore how these concepts come to life.
Awesome, let's do it.
So we've talked about all these forces and the energy involved.
Yeah, it's been a lot to take in.
But how does it all come together in the simulation?
Yeah, like, can we actually see this stuff happening?
That's the beauty of it.
Okay.
You can tweak things.
Oh, really? Like what?
You can adjust different variables
Oh, cool.
and see how it affects the outcome.
Like what kind of variables?
Well, for starters, we can change the mass of the object.
Okay.
We can adjust the initial speed we give it.
Gotcha.
We can even mess with the radius of the loop itself.
Oh, wow. So, like, we could make a really tiny loop or a giant one.
Exactly.
And the simulation shows us what happens.
This shows us how those changes impact the motion,
Whether the object actually makes it all the way through the loop.
or whether it, crashes and burns.
Ooh, crashes and burns. That sounds kind of exciting, actually.
It's all part of the learning process.
So, let's start with the mass.
Okay.
If we make the mass bigger, does that make it harder for the object to get through the loop?
That's a great question.
I mean, it seems like it would.
You would think so.
Yeah.
But remember, gravity affects all objects equally.
Right, right. Regardless of their mass.
Exactly. So while a heavier object will have more inertia.
Inertia, meaning it's more resistant to changes in motion.
Right. But it also experiences a proportionally greater gravitational force.
So those two things kind of cancel each other out.
In a way, yeah. They balance each other out.
So changing the mass doesn't really affect whether it makes it through the loop.
Not directly, but here's where it gets interesting.
Okay, I'm listening.
The mass does affect the forces involved.
How so?
A heavier object will experience greater forces.
Oh, I see. So the normal force from the track will be stronger.
The normal force from the track.
And the gravitational force pulling it down.
Exactly.
Okay, that makes sense.
So even though a heavier object might still make it through the loop,
Right.
forces acting on it would be more intense.
Which is something you'd have to think about if you were designing a real roller coaster. Right?
Absolutely. Engineers have to carefully consider these factors.
I mean, you don't want those forces to be so strong that the track breaks or the riders get hurt.
Exactly. They have to make sure the structure can handle those forces.
And that the riders have a safe but thrilling experience.
Right. It's a delicate balance.
Okay, so we've messed around with the mass.
Uh-huh.
What about the initial speed? I have a feeling that's going to be pretty important
You're absolutely right. Initial speed is key.
because the object needs enough energy to get up and over that loop, right?
The object needs enough kinetic energy at the start
Yeah.
to make it up and over that loop.
Okay.
If it's going too slow,
It's just going to fall back down.
gravity's going to win the battle,
Yeah, that makes sense.
and it'll stall out before reaching the top.
It's like trying to ride a bike up a really steep hill.
Perfect analogy.
If you don't have enough speed, you're just going to roll backwards.
And in the simulation, you can actually see this happen.
Oh, really?
You can give the object a little nudge.
Yeah.
It might make it partway up the loop,
Right.
but then it'll fall back down.
Okay.
Or you can give it a big initial boost.
And it just zooms through the loop.
It'll zoom through the entire loop with no problem.
So it seems like there's a sweet spot.
There's a sweet spot for the initial speed.
Yeah.
Not too slow, not too fast.
Where the object just barely makes it through the loop.
Exactly.
What happens in that scenario?
That's where things get really exciting.
I like exciting.
Remember we talked about that moment of zero normal force at the top of the loop?
Yeah, where it's like weightless for a second.
Well, when the object has just enough speed to make it through,
Right.
that's when that zero normal force moment happens.
So it's like right on the edge.
It's teetering on the edge.
It's like defying gravity for just a split second.
Just barely defying gravity.
That's got to look pretty cool in the simulation.
It really does. And it highlights
Yeah,
just how delicate that balance of forces and energy is.
that's so cool.
It is.
So we've talked about mass, we've talked about initial speed.
Uh-huh.
You mentioned the radius of the loop before.
Yeah.
Does that affect things too?
Absolutely. The radius of the loop is another crucial factor.
Okay, so how does that work?
A smaller loop requires a greater centripetal force.
Centripetal force being the force that keeps things moving in a circle.
Yeah, it's what keeps things moving in a circle,
Right.
always directed towards the center of the circle.
Okay, so a tighter loop means you need a stronger centripetal force
Exactly.
to keep the object moving in that path.
Exactly.
Does that mean you'd need a higher initial speed to get through a smaller loop?
Think about it this way.
Okay.
If you're swinging a ball on a string,
Yeah.
it's easier to keep it going in a circle
Yeah.
if you have a longer string.
Right.
But if you shorten that string,
You got to swing it faster
you need to swing it faster.
to keep it from falling.
Exactly.
So the radius of the loop is like the length of the string.
It's like the length of the string,
A smaller radius means a tighter turn,
the tighter turn.
which requires more speed to keep the object from falling.
Precisely.
And the simulation lets you play with all this stuff.
The simulation lets you experiment with all of this.
That's awesome.
You can make the loop bigger or smaller
And see what happens.
and see how it affects the required initial speed.
And the forces involved.
Exactly.
This simulation sounds so cool.
It is.
It's like you could spend hours just testing different scenarios and seeing what happens.
You definitely could.
That's what makes it such a valuable learning tool.
It takes these abstract physics concepts
Yeah.
and makes them tangible and interactive.
You can actually like see them in action.
Exactly.
So we've talked about mass, initial speed, radius of the loop. It seems like all these factors play a role in whether or not the object actually makes it through the loop.
They all play a crucial role.
But we've also been talking about this in the context of roller coasters.
Right.
So I'm wondering how those like thrilling rides we experience in real life
Yeah.
incorporate all this physics.
That's a great question. And it brings us back to that idea of balancing thrill and safety.
Oh, yeah. You don't want it to be too crazy.
You don't want it to be too crazy.
You want it to be exciting.
Right, exactly.
Yeah.
Roller coaster designers,
Yeah.
they use all these physics principles.
To create rides that are both exciting and safe.
Yeah.
So it's not just about building a crazy loop and hoping for the best.
It's not just about building a crazy loop and hoping for the best. There's actual science behind it.
They actually have to like calculate everything.
They have to carefully calculate the forces involved.
Wow.
Making sure the track can handle the stresses.
Right.
And the riders can tolerate the G-forces.
The G-forces, that's that feeling of like being pushed down in your seat or feeling weight.
Exactly. And those sensations
Yeah.
are directly tied to the normal force we've been talking about.
Oh, right.
Remember, the greater the normal force,
Yeah.
the heavier you feel.
Okay, so to make the ride really thrilling,
Mm-hmm.
the designers would want to create sections with really strong normal forces.
Exactly. And they do that by using a few tricks.
Oh, like what?
They might make the bottom of the loop tighter,
Okay.
which increases the centripetal force,
Right.
and therefore the normal force.
Gotcha.
They might also give the coaster a big initial boost of speed
Okay.
going into the loop.
So they're basically manipulating those physics principles we've been talking about
Precisely.
to create those heart-pumping drops and turns,
Exactly. And they also have to consider the opposite,
which is...
creating sections where the normal force decreases.
Oh, right. To give you that feeling of weightlessness.
Yeah, giving the riders that feeling of weightlessness.
Or even a brief moment of airtime.
Exact.
So it's this constant back and forth.
It's a delicate dance
Yeah.
between maximizing those forces for thrill
Right.
and keeping them within safe limits.
It's amazing to think that all this physics is going on behind the scenes of those rides.
It really is.
Like, we're just enjoying the ride.
You're just enjoying the ride.
But there's all this science happening.
All the science is happening behind the scene.
It's mind-blowing.
It is. And you know, this conversation has gotten me thinking about other examples where these principles come into play.
Oh, yeah. Like what?
Have you ever thought about how these same forces and energy transformations
Yeah.
apply to something as grand as satellites orbiting Earth?
Wait, are you saying that those tiny little satellites way up in space
Yes.
are experiencing the same kind of physics as a roller coaster?
That's exactly what I'm saying.
Okay, now you've really got my attention. Tell me more. Okay, so those satellites orbiting Earth. Yeah. You're saying they're experiencing the same kind of physics as a roller coaster.
It might seem like a stretch, but the underlying principles are surprisingly similar.
I am having trouble wrapping my head around this.
Well, think about it this way. A satellite orbiting Earth It's essentially in a constant state of free fall.
Free fall. Like it's just falling all the time.
Just like that moment at the top of the roller coaster loop,
Oh, okay.
when the normal force disappears and you feel that brief sensation of weightlessness.
So you're telling me satellites are constantly falling?
They are indeed falling, but
That they don't crash into Earth?
they're also moving forward
Okay.
with enough speed, what we call tangential velocity,
Tangential velocity.
that their trajectory curves around the Earth.
So it's like they're constantly being pulled towards Earth by gravity,
They are.
but they're moving so fast sideways that they keep missing the planet.
You got it.
It's like, imagine throwing a ball horizontally.
Okay.
The harder you throw it, the farther it travels before hitting the ground.
Right.
So a satellite is kind of like that ball, but it's thrown with enough force.
It's thrown with enough force that its path curves around the Earth,
That's wild.
and it stays up there in orbit.
So it's this perfect balance.
It is a perfect balance between their downward motion due to gravity
Yeah.
and their forward motion that keeps them from crashing down,
So Earth is like constantly tugging on the satellite.
like keeping it on an invisible leash.
But the satellite's zooming along fast enough to stay out of reach.
That's a great way to visualize it.
Uh,
And just like with a roller coaster,
there's that interplay of potential and kinetic energy.
there's this interplay of potential and kinetic energy.
Okay.
As the satellite gets closer to Earth,
Yeah.
its potential energy, which is related to its height, decreases.
Okay.
And its kinetic energy, which is related to its speed, increases,
So it speeds up.
causing it to speed up.
And as it moves farther away.
The opposite happens.
So it's that same energy dance we've been talking about.
The same energy dance
Just on a much grander scale.
on a cosmic scale.
It's amazing how these like basic physics principles
It really is
will
remarkable
apply to so many different things.
how these fundamental principles of physics apply across such a vast range of phenomena.
From a roller coaster to a satellite.
From a simple ball swinging on a string
Yeah.
to the complex motion of celestial objects.
This whole conversation has really changed how I see the world.
That's the beauty of physics, isn't it?
Like now I'm going to look at everything differently.
It gives you this deeper understanding of how things work,
Roller coasters, pendulums, even the moon.
and it makes you appreciate the elegance and interconnectedness of the universe.
I'm going to be thinking about forces and energy transformations everywhere I go.
I love that.
Well, this has been an incredible journey.
It has.
We started with loop-the-loop roller coasters.
Hey, you did.
Then we dug into this awesome simulation.
Mm.
And now we're talking about satellites orbiting Earth.
Who knew physics could be so much fun?
And we just scratched the surface.
There's a whole universe of physics out there waiting to be explored.
Well, on that note, I think it's time to wrap up this deep dive.
Sounds good.
But before we go, I want to thank you for taking us on this wild ride through the world of physics.
It's been my pleasure. Keep those curious minds engaged and never stop exploring the wonders of our universe.
And to you, our listeners, thanks for tuning in. We hope this deep dive has sparked your curiosity and giving you a new appreciation for the physics of fun. Until next time, keep on learning and keep on diving deep.